All right, example 13 is a little bit jazzy. We have the system x over 2 plus y over 3 is equal to 7 over 6, and 2x over 3 plus 3y over 4 is equal to 5 over 4. So at first we might be a little upset, oh no, we've got fractions. Fractions complicate everything. I'd like to show you a trick, and this is a trick that's going to come back and be very useful to us in chapter 6. We call this trick clearing the denominators. Here's what I'm going to do. And let's just look to start at equation 1. X over 2 plus y over 3 is 7 over 6. Now I'm going to inspect the denominators of each term in the equation. And I'm going to go looking for the least common denominator. So the least common denominator amongst 6, 3, and 2. It happens to be 6. Now look what I'm going to do. I'm going to take 6. I'm going to multiply every term by 6. Recall earlier we said so long as I multiply every term in the equation by the same thing, I will end up with an equivalent equation. Equivalent in this case means that the solution set is going to be the same. All right, look what's going to happen here. I have got 6 times x over 2. Remember, this is 6 over 1. What's going to happen here? Well, 2 divides 6. So a little bit of fraction reduction. 2 divides 2 becomes a 1. 2 divides 6 becomes a 3. This gives me 3 times x. So 3x. We'll do the same thing here. 3 divides 6. 3 divided by 3 is 1. 3 divided by 6 is 2. That gives me 2y. Finally, I've got 6 over 6. 6 over 6 is 1. So that equals 7. I have now manipulated this equation so that there are no fractions. I'm going to do the same thing to the second equation. Here comes equation 2. I have 2x divided by 3 plus 3y divided by 4 is equal to 5 over 4. My denominators are 3 and 4. The least common denominator for all of these, also known as the least common multiple, it's going to be 12. All right, I'll just divide everything by 12. 12 times 2x divided by 3 plus 12 times 3y divided by 4 equals 12 times 5 divided by 4. And what's going to happen? Well, 3 divides 12. 1 and 4. That gives me 4 times 2x, so I have 8x. Here I have 4 divides 12, 3. 3 times 3 is 9, so that becomes a 9y. Last thing here, 4. Again, that's 3. I get 15. So I have now a new equivalent system with no fractions. I'll call this equation 3, and I'll call this guy equation 4. I will solve the system using equations 3 and 4. So I proceed with my algorithm, make sure everything's written in standard form. It is. Step 1 is check. Let's see which variable I want to eliminate. Looks like there is no difference here. They're both, that's positive here, positive here, positive here, positive here. So I don't have any opposite signs. I have a 3 here and an 8 here, a 2 here, and a 9 here. So in fact, it's not a very convenient system to solve using elimination, but we can still do it. I will choose to eliminate y. And I can see that I'm going to need to manipulate both equations. I will multiply equation 3 by 9. If I multiply equation 3 by 9, I get 9 times 3, which is 27x. 9 times 2, 18, y, and then 9 times 7, which gives me 63. I have another new equation. I'll call this equation 5. Equation 4, you may have guessed, I'm going to multiply it by 2, but not just 2. I will multiply it by negative 2. I multiply it by negative 2. Eight is 16, so that'll give me a negative 16x. 2 times 9, 18. It's negative. That's a negative 18y. And a negative 2 times 15, negative 30. Now I have plus 18y over here, minus 18y over here. I'll call this thing equation 6. What am I going to do now? I'm going to add equations 5 and 6. So I'll take 27. I'll take 27x plus 18y equals 63. And add to that a negative 16x, negative 18y, negative 30. In this column, 27 minus 16 gives me a positive 11x plus 18y minus 18y, the 0 that I wanted. And then take 63 and subtract 30, that gives me 33. I now have 11. X is equal to 33. I can divide both sides by 11. I find that x is 3. All right, I'm going to put this x equals 3 into one of my equations. Since they should all be equivalent, I'll just use the equation 3x plus 2y equals 7. As long as we haven't made any mistakes, each of these equations should have the same solution set. So if I put in the 3 for x, I find 9 plus 2y is equal to 7. Subtract 9 from each side. I find that 2y is equal to negative 2. I divide both sides by 2. This tells me y must be equal to negative 1. So my proposed solution is x equals 3, x equals 3, y equals negative 1. All right, I manipulate this system a lot. So I'm going to take this proposed solution back to my original equations and make sure that they actually work. So my first original equation said x divided by 2 plus y divided by 3 should give me 7 divided by 6. Plugging in, I have 3 over 2 plus, that'll be a negative 1 over 3. I very much hope that gives me 7 over 6. I am going to need to get a common denominator. We've already discovered that that was 6. So I will multiply my first term by 3 over 3 in order to turn that into a 6. I'll multiply my second term by 2 over 2 in order to turn that into a 6. And I needn't do anything to the other side. Does this give me 3 times 3 is 9? Over here, so I get 9 over 6. This is a minus, right? Plus a negative just means minus, so I'll just write minus. 2 times 1 is 2. That's also over 6. 9 minus 2 is indeed 7. We're very hopeful. Looking good. All right, now we're going to check in the second equation. The second equation was 2x over 3 plus 3y over 4 equals 5 over 4. I'm going to enter my proposed solution here. I have 2 times 3 over 3 plus 3 times negative 1 over 4. I very much hope that that is 5 over 4. Now look here, 3's are going to cancel, which means what I have here actually is 2. That becomes a negative 3. I'm adding a negative. That's a subtraction. That's 3 over 4. So 2 minus 3 over 4. I hope that's 5 over 4. I don't know. I need to put 2 over 4. So I will just multiply 2 by 4 over 4. Gives me 8 over 4 minus 3 over 4. And 8 minus 3 is 5. And I am pleased and can write my solution is x equals 3, y equals negative 1, or equivalently, the ordered pair 3, negative 1. That's going to be it for us for sections 3.1 and 3.2. Next time we come back, we're going to look at applications involving this. So we're going to do some real world style applications.